All right, let's get started. So today we'll continue our discussion of transfer learning. Before we start, a few logistical notes. So I know that the proposal was pretty recently, but keep in mind that your project milestone is due 2 weeks from now. So hopefully you're all getting started on your projects now that the homeworks are done and making some progress. So do check out the instructions for the milestone. Those are on Piazza. And please make sure that you're getting started. A number of you have asked us about homework 3 grades. So we've already sent out homework 2 and homework 4 grades. And that was because the GSI has got things a little out of order. So don't panic. Homework 3 is not yet graded. So if you didn't receive an email about that everything is fine. Just we'll get that done for you soon. So we've sent out homework 2 and homework 4, but not homework 3 yet. OK. So when we started our discussion of transfer last week, we talked about how there are sort of 3 broad categories of methods that we'll discuss. Forward transfer methods that train on a source domain and then attempt to transfer to a target domain. Multitask transfer methods that train on a set of different tasks and either attempt to transfer to a target task or actually try to accelerate all of the different tasks through mutual sharing of information. And then the third category is meta-learning algorithms, which actually also operate in the multitask setting, but actually attempt to learn how to learn. So this third category we'll probably cover on Wednesday. And then today, I'll finish up the discussion of forward transfer and talk about multitask transfer learning algorithms. And just as a reminder, this is the same as what I said last week, is that at this stage, we're really talking about kind of state-of-the-art research work. There isn't a single kind of known perfect solution. This is really more meant to be a survey of recent research papers, partly to kind of jog your ideas for your final project, and also to give you an overview of the state of the literature. OK, so let's resume our discussion of forward transfer. So on Wednesday last week, we talked about how you could just train on your source domain, attempt running your policy on a target domain, and basically hope for the best. And sometimes this works. Sometimes you had enough variability in your source domain and things just work right out of the box. But usually there's not any way to, there are no promises on this. So one of the things you could do, one of the simplest ways of performing transfer is to fine-tune. It's to train on some source domain, and then when you go into the target domain, start from what you had in the source domain and train some more. Fine-tuning is a very effective way of doing transfer in fully supervised domains like computer vision. But in reinforcement learning, there are a few issues with fine-tuning that we discussed last week. They include things like the entropy collapse, where if you have a policy, that policy ceases to explore once it converges. So when you put it in a new target domain, it might not actually learn very much because it's not exploring anymore. We talked about how maximum entropy objectives can really help facilitate transfer and discussed a few results there. And then we talked about architectures that are specifically designed to be better suited for fine-tuning, like progressive networks, which address some of the overfitting and expressivity problems basically through the design of the network architecture. So right at the end of Wednesday's lecture, we left off on this topic. What if we can actually manipulate the source domain? So when we talk about fine-tuning, we typically assume that the source domain is fixed. That's what's given to us. And then we have to basically make do with what we have. But in many practical transfer settings, we actually get some amount of control over the source domain. And our goal is to do well in a target domain that we do not control, where we have, let's say, very limited opportunity for experience. What if we can design the source domain and we have a difficult target domain that we don't control? So this is very often the case, for example, if we're doing simulation to real-world transfer. So if we'd like to train our agents in a simulated environment, whether it's a simulation of a robot or a data center or some kind of logistics system, and then transfer to a real environment that is qualitatively similar, but perhaps quantitatively a little bit different. So the general idea, if we have the ability to manipulate the source domain, is that the more diversity we see at training time, the better we will transfer. So if you don't know exactly how much your robot will weigh at test time, if you train on robots of different weights, you're more likely to succeed than if you train on just one weight that is the wrong weight. And the last method that I discussed on Wednesday, which I'll very briefly recap again, is this approach called EP-opt, which operates on the principle of maintaining distributions over parameters of a system. So the example that I gave before was that maybe you want to learn a policy for this little monopod hopper, and maybe the size of the hopper, the weight, or the inertia will be a little different at test time. If you train on a variety of different physical parameters, you're more likely to effectively transfer. This by itself is not that surprising, but some of the things that were interesting observations in this work are that, obviously if you train on the right mass, like if you have mass equals 6 at test time, then training on masses close to 6 works the best, and then performance degrades as the mass is more incorrect. But surprisingly, if you train on a variety of masses, so this bell curve is showing the distribution of masses at training time, you'll actually succeed on a variety of masses at test time too, with actually very little degradation in overall performance. So traditionally, the conventional wisdom in, let's say, robust control is that if you train for robustness, meaning you train for worst-case perturbations or worst-case model errors, you will obtain conservative policies that are more robust, but at the cost of performance. That is almost certainly the case in some problems, but one of the interesting observations in this work is that, at least for the kind of simulated robotic systems considered here, training deep neural network policies seems to a large degree actually mitigate that issue, that if you have more expressive policies, they can achieve very good performance and robustness. Now, obviously, this is going to extend up to a point. At some point, you might have a system that is so complex that this just wouldn't happen, but it's an interesting thing to keep in mind if you're considering simulation to real-world transfer, that more expressive policies can actually get you robustness, perhaps without sacrificing as much of the performance. And then at the end, we talked also about unmodeled effects, how if you have physical parameters that changed at test time that were not even varied at training time, if enough other parameters were varied, then you might still obtain some degree of robustness. Okay, so that's the brief summary of EP-opt, and this is where I left off on Wednesday. Now, one of the things about EP-opt is that it is not attempting to figure out what are the physical parameters of the current environment. So it's simply relying on the diversity at training time to build a policy that can succeed under whatever conditions happen to exist at test time. We could imagine building a reinforcement learning system that explicitly attempts to figure out what situation it's in. So this is another paper from Georgia Tech by Yu et al. Called Preparing for the Unknown. And in this work, they propose an architecture that actually combines a deep neural network policy with a deep neural network system identifier. So if there are some parameters of your simulator, in their case, they're also dealing with simulated robots, but the method is actually fairly generic in that sense. So whatever system you have, whatever physical parameters it has, those are being denoted by mu. So this might be, for example, the mass of your robot or the friction coefficient. And they're training a policy pi that chooses actions based on the state x, but also based on mu. So the policy is actually told, you are now controlling a robot with a mass of 67 kilograms. Take your action. And then they train a separate network called phi, which is actually a recurrent neural network. It actually takes in a history of past states and actions and attempts to predict mu. So again, this is targeting a simulation to real-world transfer style domain where you assume that in the source domain at training time, you do know the true parameters of mu, so you can actually build this predictor, and you can train it jointly with your policy so that it predicts physical parameters that are well suited for your policy to take good actions at test time. So and then the policy just takes in the physical parameters. So this is a little visualization and another kind of monopod hopper that they test on. And then they also vary some physical properties of the system. In this case, it's the offset of the center of mass from the middle of the robot. And they find that their method, this UP OSI, the red curve, is actually able to extend to a further range of physical variation. In fact, pretty close to what happens if you give it the true physical parameters, which is the green curve. So this is sort of combining simultaneous system identification and policy learning to try to explicitly identify the conditions of the target domain. Now, one of the important points here is that the system identification network is trained together with the policy, which means that it doesn't necessarily, the policy might succeed not just because it's getting the true parameters, but because it's getting whatever parameters it needs to take good actions. So does anybody have any questions about this method? Yes?
No, never mind.
Okay, let's continue. Actually, it's a good thing that I didn't get to this stuff on Wednesday, because actually since then a new paper came out which actually essentially extends and applies this class of approaches to a real physical system. So the two papers that I discussed before both are aimed at simulation to real-world transfer, but they evaluate in simulated settings, essentially simulation to simulation transfer. This is a new paper that I don't have that much to say about it. It's actually brand new, but this is by Shuai-Bin Peng and collaborators, who's actually a student in this class. Here they have a real robot executing a task in the real world that was trained in simulation using this kind of physics randomization style approach. And the method is sort of a cross between the last two, so it actually uses a recurrent policy, but doesn't explicitly attempt to predict the physics parameters, so it's sort of implicit system identification. And the task is to push a little puck to a location, trained in simulation. Okay. So far, we talked about potential discrepancies in terms of the physical aspects of the environment, in terms of things that are perhaps low-dimensional, but can differ systematically from the source domain to the target domain. One of the things that we can do is we can also think about how some of these ideas extend to much more complex input spaces, like vision and images. So this is another work that actually studies many of the same principles for simulation to real-world transfer, but now for the case of vision-based control of a real-world quadrotor in this case. So the goal in this work is to make this little quadrotor follow hallways using a monocular camera. And the approach is basically based around trying to set up extremely diverse simulated environments. And here, a very interesting question to explore is, well, if you're going to choose to design your simulator, should you choose to design a simulator that's very realistic, or is the benefit of diversity and randomization so important that you can actually design a much less realistic simulator, but one that is highly randomized, and still attain successful transfer? So in this work, the authors designed a range of very different simulated environments that all, they don't individually look very realistic. They sort of look like maybe video games from the late 90s, but they're highly randomized. So this is like textures mined from the internet and random textures placed on walls and so on. Many of them are not realistic, so you end up with things like grass on walls and so on. But because of the visual patterns that are conserved across these domains, those are the ones that are the most general, such as vanishing points at the ends of hallways. The policy is actually able to learn pretty decent navigational strategies. So here's a little animation of the training environments, and they have some randomly placed furniture, lighting, and so on. And here's an animation of a deep neural network policy that was trained with reinforcement learning in those simulated domains and is then deployed in the real world on a real quadrotor. You'll see this red dot in the middle of the screen, and the red dot is actually the action. So the action space for the system is to pick a point on the image, and then the quadrotor uses an onboard velocity controller to basically fly in that direction. So if you see a red dot, that's basically where the policy is choosing to direct the flight at any given time. It doesn't actually necessarily end up going there because the flight controller on the quadrotor is imperfect, and there's wind gusts and so on. So here's the animation. You can see it's not perfect, so sometimes, especially with windows, it has a tendency to sometimes move the dot over windows and get a little distracted. But on the whole, it actually does a pretty good job of flying the quadrotor down this hallway and keeping it centered. It does make some humorous mistakes sometimes, so one of the things that happened was that in the simulated environment, there aren't any reflections. And if it sees a very reflective door in the real world, it will actually direct its flight towards that because it thinks that there is something on the other side of that door that it can go to. So maybe not, a little bit like how a bird might fly into a window. So maybe the story here really is that enough diversity in the source domain can go a long way towards enabling transfer, but you do have to make sure that you avoid sort of pathological regularities like the lack of reflections. Now, since this work, there have been a number of also follow-up works that have applied this idea to domains like localizing objects in an image and also having robots manipulate objects. So these are robotic manipulation works that are also making use of the idea of randomizing the appearances and properties of objects in simulation to enable transfer to the real world. Now, so far, we've talked about pure zero-shot transfer, where we have our algorithm learning in the source domain so that we can succeed in some unknown target domain. So for all these simulation to real-world transfer methods, they don't get to know anything about the real world. They're just given the simulator. We get to design the simulator. But then they have to succeed in the real world as soon as they're placed into it. This is, of course, in general not possible. So you can always pick a target domain that is so different from anything that you trained on that you just have no chance of succeeding. So what if we actually got to peek at the target domain? So what if we could give our algorithm a little bit of information about the target domain and then lots of information about the source domain? So, for example, what if we gave it all of this experience of flying around in a simulated environment, but also showed a little bit of what happens in a real-world environment? Can we do better in that case? Can we somehow take advantage of very limited target domain data? This is a very recent area of study in deep reinforcement learning. There's actually quite a bit of work on this in older, kind of more traditional reinforcement learning literature, but in deep reinforcement learning, this is actually fairly new, and there are a few works that have studied this, largely inspired by domain adaptation techniques in computer vision. So one example, this paper, which uses an adversarial domain adaptation method. So the idea here is that you have a little robot, and it needs to perform some manipulation task. In this case, it's hanging a little rope on a grocery scale. And the simulation doesn't look, again, it doesn't look very realistic, but it has many of the same kind of qualitative properties. So it has the same objects. The general nature of the physics is different, but it's sort of qualitatively similar, meaning if you tell it to go left, it'll go left, but maybe at a different velocity. And the way that simulated and real-world data is combined in this technique is that and this is mainly dealing with the discrepancy in the perception, is that there's a convolutional network that's processing the images, and that convolutional network has shared parameters across the simulation and the real world, and an additional loss function that says, for the features inside that convolutional neural network, the features should not be sufficient to distinguish between simulation and reality. And the way that's enforced is by training this thing called the confusion loss, which is basically a classifier that tries to look at the features inside the convolutional neural network and guess, are these the features of a simulated image or a real image? And then the gradient of this classifier is reversed and back-propagated back into the convolutional layers, which basically asks them to come up with features that will fool the classifier, that will make the classifier unable to figure out whether it's looking at the features of real images or the features of simulated images. Now, this confusion loss is providing domain adaptation machinery just for the perception, and it's not attempting in any way to account for the physical discrepancy. So this is, as I said, inspired by techniques from computer vision, and all it's trying to do is arrive at invariance. So it's saying that if there's something between simulation and real that doesn't match up, just ignore it, which in some cases is a reasonable approach to take. Another recent method that looks at simulation to real-world adaptation, also inspired by techniques in computer vision, is this paper by Busmalis et al., which instead of, or actually in addition to trying to regularize the features with this kind of confusion loss, it also attempts to make simulated observations themselves look more like real-world ones. And this is achieved by means of a generative adversarial network, which actually takes in simulated images. So this is a robotic grasping task. This is a simulation of a robot picking up objects from a bin. These are simulated images, and the generator actually attempts to convert them into images that are indistinguishable from real ones. The discriminator, which is the second classifier network, looks at, now it doesn't look at features, it actually looks at pictures, and it looks at pictures that are either from the real world or the output of this generator, and tries to predict, are they real or fake? And then the generator is trained to fool the discriminator. So if the discriminator can't tell from looking at the generated image whether it's a real image or a fake one, then that image is likely to have it's likely to have had all of the artifacts from simulation replaced with things that look more like the real world. So then these transformed images can be fed into the policy, which is trained on the transformed images from the generator and a limited number of experiences from the real world. So here's a little illustration to show this in action. So this is a simulated sequence of a robot picking up an object, and the thing that you're seeing at the bottom is actually that same video transformed by the generator, and here you can see the half and half split. So to us, it's fairly clear this is obviously not a real video, but you can see that there's actually quite a bit of modification to it. Let's watch that one again. Quite a bit of modification to it that does make it look a little bit more realistic than the simulation. And this method actually for policy transfer, it also combines this with the adversarial loss in the previous work on the features of the policy itself also. All right. Does anybody have any questions about these kind of domain adaptation techniques in reinforcement learning? Okay. So a summary of forward transfer methods. So we talked about pre-training and fine-tuning. We talked about how standard fine-tuning with reinforcement learning is not quite as straightforward as it is in supervised learning, and how things like maximum entropy can help there. We talked about how we can specifically modify the source domain to make it better suited for transfer. And here we saw that randomization can actually help a lot. So the more diverse the source domains are, generally the better you'll be at being able to transfer. And we talked about how we can use modest amounts of target domain data to perform some sort of domain adaptation. For example, you can make the features in your network such that a classifier can distinguish between the two domains, or you can actually directly modify the observations to make them indistinguishable between the source and target domain. Now, that said, these kind of domain adaptation techniques only provide invariance. So it basically assumes that anything that is different between the source and target domain is functionally irrelevant. Meaning that if there's some object or some kind of property in simulation that is not present in the real world or vice versa, you can simply ignore it and still succeed at the task. Now, clearly this is not the case in general, for the kind of tasks you might want to do. So for example, if you have a simulation of a car driving around on the street and maybe your simulator doesn't simulate pedestrians, well, you don't want to just ignore the pedestrians in the real world. You need to somehow actually account for those things. So these methods provide invariance, but they do not try to pick out functionally relevant variation between the two domains, and that's kind of at the frontier of current research in this field. Okay, some suggested readings on forward transfer. So these are all the papers that we covered last week and today. This is the paper on maximum entropy policies. This is the progressive neural networks paper that proposes this architecture that's a little better suited for fine-tuning. This is the EP-opt paper. This is the paper with the quadrotor flying through the hallway. These are some of the, or I guess this one is a paper that I mentioned briefly that also randomizes the appearance of objects in simulation for a manipulation task. This is the domain adaptation paper with the robot and the grocery scale, and this is the paper with the grasping robot and the transformation of simulated images into real-world images. So if you want to learn more about recent research on this topic, check out these papers. And now we'll take a short 3-minute break, and when we come back, we'll talk about multitask transfer methods. So see you back here in 3 minutes. All right, let's continue. So back to our roadmap. So we finished our discussion of forward transfer methods, which operate on a single source domain and then attempt to transfer to a single target domain. And now what we'll do is we'll discuss multitask transfer methods. These are methods that will aim to train on many tasks and then either transfer to a new task or actually just have all of the tasks trained faster by virtue of being trained together. And we'll talk about a number of different classes of methods that make use of multitask transfer. We'll talk about how model-based reinforcement learning can provide for an appealing vehicle for multitask transfer. We'll talk about model distillation, where we can actually combine reinforcement learning on multiple different tasks with supervised learning in kind of imitation learning style. We'll talk about contextual policies, which are policies that take as input some sort of specification of the task that they're supposed to do. And then we'll talk about architectures that are well suited for multitask transfer, specifically modular neural network policies. So let's discuss a little bit why we might want to consider multiple source domains instead of a single source domain like before. So far we've seen that generally the more diversity you have in your training environment, the more likely you are to have effective transfer. And when we talked about things like simulation to real-world transfer, we were in this situation where we had to basically design this diversity into our system somehow. So if the source domain is something that you're actually manually designing, then you can design it in such a way that it is more varied, more complex, and therefore facilitates transfer, like the simulation to real-world transfer case. But what if we instead had access to many different tasks that our agent could attempt? Now, maybe we don't have to work so hard at designing a single domain where it can do the tasks that it wants to do in very diverse settings, but we can instead use the fact that these multiple tasks are, just due to their nature, are going to get the agent to cover various different situations and see what happens in different settings. The trouble is that these are now different tasks, so you can't directly do the thing that you were doing to solve these different source tasks because you were trying to do something different. So in a sense, this is a little closer to what people do, because when you want to figure out how to solve a new problem, it's not that you're drawing on your experience of solving that exact same problem before. You're trying to figure out what bits and pieces you can take from other things you've done in the past and then repurpose them for a new task that you need to be able to perform. But of course, it's substantially harder because the past tasks don't directly tell us exactly what we need to do to solve this new task in the target domain, and there might be some negative transfer and some positive transfer. Some of the things from those past tasks might be useful, and some might not be. So if all the past tasks are all different, is there something that they all have in common? Is there some particular feature that we could grab from all the past tasks and use without concern for whether the task discrepancy is going to cause us problems or not? So one idea that we have is the laws of physics. So if your agent is operating in some kind of universe, whether it's a robot operating in the physical world or an agent that's doing something on the internet operating under the rules of that environment, there's some kind of equivalent of the laws of physics, some kind of dynamics that are conserved across all the tasks that your agent is attempting to do. So you can have the same robot doing different chores, the same car driving to different destinations. If all the different tasks in your multitask learning setting exist in some sense in the same universe, that universe is governed by some rules, and you can attempt to extract those rules. So a simple version of this would be to simply train a model on your past tasks, a predictive model that tries to predict the next state given the current state in action, and then use it to solve a new task. And this is essentially just standard model-based reinforcement learning. So the short version of idea one is that, well, if you're in a multitask transfer setting, one of the things you could do without having to worry too much about transfer is to just do model-based reinforcement learning, because your model, just from the start, is much more likely to transfer than your policy because the model is independent of the task that you're trying to perform. This by itself might not necessarily be enough, however, because the model is actually still trained on some kind of data, and that data is collected while you're attempting to do a task. So if you remember the lectures on model-based reinforcement learning, we talked about this version 0.5 of the model-based RL algorithm, where you actually fit your model, figure out the corresponding behavior, execute that behavior in the real world, and gather more data to update your model. And that was necessary in order to mitigate the domain shift problem in model-based RL. So because you're mitigating the domain shift problem while solving some particular set of tasks, the kind of states that you'll see for those past tasks might still not match the new destination task. So even though you're not going to get negative transfer, the laws of physics are still the laws of physics, you might not actually be able to get a good model from the source tasks if they visit different parts of the state space. So a more complex version of using model-based RL for transfer is to adapt or fine-tune your model to the new task. So just because you have a good model that succeeded the past task does not mean that it will succeed right away for a new task, but it likely will serve as a very good starting point. And there are a number of ways that you can use a model that was trained on past tasks for a new task, including many of the tools that we discussed in the previous section of forward transfer, like fine-tuning. Since the model is trained with supervised learning, it's actually much more amenable to fine-tuning. I'll actually present a brief discussion of some recent work that does something a little different than fine-tuning. So here, this is a paper, again, on robotic manipulation, where the goal is to perform one-shot learning with model-based prior. So if you remember from last week on Wednesday, one-shot means that you get to attempt the task once in the target domain after a large amount of experience in the source domains. And the way that this method is going to work is it's going to see some source domains. In this case, these are different assembly-style tasks. So the robot might put some ring on a peg, some nail in a little hole, and some Lego blocks together. It's going to learn dynamics models from these, and then it's going to attempt a new task, like putting a little gear assembly together. So there are a lot of qualitative similarities between these tasks, but the gear assembly is, in some systematic way, different from many of the things that it saw before. So what the robot is going to do here is actually use that prior experience to build a model, but then use that model as a prior for a new model in the target domain. So the idea is that you have a large collection of source domains, and you want to use them to accelerate, to perform one-shot learning in a target domain. And you're going to build a dynamics model, a model that takes in this case, it's actually 2 previous states and 2 previous actions, and predicts the next state. The reason that it's 2 states is a little nuanced, but the reason is actually that if you want to detect a collision, 2 states really helps, because then you see your previous state, you were going fast, your new state, you're going slow, and in between you kept pushing, that means that you hit something. So in these kinds of partially observed settings, having the 2 states available there can be really useful. And then this model is not actually directly used for planning in the target domain. Instead, it's used to create a prior that will then serve to very quickly acquire a model in the target domain using very recent, a recent batch of experience and a very fast estimation method actually based on linear models. So the details of this are in the paper, but the short version is that the prior is combined with a small amount of experience in the target domain to get a posterior estimate of the dynamics. So here, the model is not even being fine-tuned because this is just a one-shot setting. So in one shot, the model wouldn't be fine-tuned enough to make it effective. But if you had more shots, you could fine-tune it further. Yes?
Is it a prior on the neural network weights or on the...
It's actually a prior on the transition dynamics themselves. So it's a locally linear estimate of the transition dynamics. Yeah. You could also imagine constructing a prior on neural network weights, for example, building on the Bayesian neural network stuff that I discussed before when I talked about exploration. So here's a little animation of this in action, and this is a kind of a hold one out cross-validation type setting. So there are a number of tasks, and every time you see a task, it's using all the other tasks to build the prior. So for the nail, it's using the Lego block and the plane and the car as the prior, and for this one, it's using again all the other tasks. And you can see that it's not very quick, it's not very proficient at doing this task. It sort of fumbles around a little bit, and when it's fumbling around like that, it's actually acquiring more experience to try to get a better posterior estimate of the model. So again, with a Lego block, it doesn't go straight to the target. It actually gets stuck a little bit, fumbles around, but for every single time step, it's collecting more experience and improving its posterior estimate of the model. All right, yeah, so there it takes a little while to figure it out. Okay, any questions? Yes?
Is this a vision-based reward that's like getting higher and higher as it gets closer to putting it in the peg? Or?
Right, very good question. I forgot to mention the state space. So this is not using vision. This is just using the state of the robot's arm and its end effector. And the position of the target, basically where the part is supposed to go, that's provided as input. So it's just dealing with the physics. We saw model-based RL in a vision-based setting before, actually, in Chelsea's lecture earlier when she talked about video prediction. But to my knowledge, fast adaptation of those kinds of methods hasn't been done yet. So the takeaway from this is that if you're in a multitask learning setting, generally you can consider doing model-based RL, and you might expect your model to transfer better between tasks than your policy because the tasks all involve doing a different thing. Simply taking your model and using it to plan in the target domain may or may not work. The domain shift problem might prevent it from working, in which case you might consider fine-tuning or some kind of rapid adaptation technique similar to what I presented here. Okay. Now, in that setting, we were still looking at a case where we have many source tasks, and then we have one target task that we're trying to perform. Another thing that you can do in a multitask learning setting is actually imagine having multiple tasks where you're trying to solve all of them at once. So sometimes learning a model is very hard. Perhaps we'd like to learn a policy that can simultaneously perform many tasks. So taking a policy from a source task that is different and then trying to run it on a target task, that doesn't make any sense because the policy is trying to do the wrong thing. But maybe if you train the policy on multiple tasks simultaneously, it can see some experience from all the tasks, and as a result of the sharing between tasks, solve all of them more quickly. So this is a different problem setting, and that's the one that I'll discuss next. And this is a kind of a simultaneous transfer setup. Now, one of the ways that we could do this, one very naive way that actually works reasonably well in simple settings, is to construct a joint MDP. So what that means is we say, okay, we have n tasks. Each of the tasks corresponds to a different MDP. And we'll actually bake those n tasks into a single MDP using a very simple scheme. We'll just say that don't worry about idea 2 for now. We'll say that at the first time step, you have a distribution over initial states, P of S0. And you will sample an initial state, and you'll run your policy. In a multitask setting, that sample involves sampling first the MDP and then the initial state within that MDP. But then after that, you stay within that MDP. So in the first time step, you sample an MDP, sample initial state from that MDP, and then you carry out your policy. And this hybrid combination of multiple MDPs actually corresponds to another larger MDP. It's just a very peculiar one where the initial state distribution has this fairly complex structure, but then once you've picked the initial state and corresponding to the MDP you're supposed to act in, then everything is relatively straightforward. So this is a way that you can fuse multiple MDPs into one, and once you've done that, you can just run your favorite reinforcement learning algorithm. This is a very reasonable thing to do, and for tasks that are reasonably tractable, this actually can work very well. However, if these MDPs are very different, and you're already sort of at the limits of what a state-of-the-art deep RL algorithm can do, then amplifying the complexity of the problem so much can actually make it very difficult to solve. So if, for example, you imagine that each of these MDPs is an Atari game, each Atari game takes you tens of millions of time steps to solve. If you now amplify the difficulty of the problem by forcing the agent to succeed in a randomly sampled Atari game, it might simply be impractical with the best algorithms that we have today to learn a successful policy that plays all these games at the same time. It is technically feasible. There's nothing sort of fundamental preventing you from doing that. It's just sort of a problem that might be a little too hard for our current state-of-the-art methods. So idea 2, which is what I'll actually discuss next, is to train in each MDP separately and then somehow figure out how to fuse the different policies into one. And you can fuse all the different policies into one at the end of training, in which case you just get a policy that can play all the Atari games. That in itself may be useful, but it's not actually the main kind of thing we're going for. We're going for the simultaneous transfer. So what you can do instead is you can actually fuse the policies into one as you're training. So you train for a little bit, fuse them together, train for a little bit more, and so on. And that's what I'll talk about next. But at a high level, does anybody have any questions, especially about this joint MDP? Yes?
It seems like we would have to encode all of the differences between the tasks in the states, and that the dynamics and the reward function would have to be basically the same. Right.
So I think what your question is getting at is, well, okay, if you set up this joint MDP, how does your policy know what it's supposed to be doing, right? So far, we haven't addressed that at all. So if you imagine, let's say, your policy is trying to play different Atari games, well, it can probably know what it's doing just by looking at the picture. So if it sees something that looks like Pong, it knows it's supposed to play Pong. If it sees something that looks like Breakout, it knows it's supposed to play Breakout. But in some cases, this might not be possible. So in some cases, maybe you have your robot, it goes into your home, and today it has to do the laundry, and tomorrow it has to make the coffee. Unless something tells it what to do, it has no way of knowing. So far, we're not addressing that, but actually next I'll talk about contextual policies that do address exactly that problem. So for now, let's just assume that there's something, as you said, in the state that lets you guess what you're supposed to be doing. Okay, So let's talk about idea 2. Idea 1 is very straightforward, and in fact, if you're trying to address a multitask setting where you want the simultaneous transfer, idea 1 is a very reasonable thing to start with. If you attempt idea 1 and it doesn't work, then let's talk about idea 2. And this is based on 2 papers that came out, I think, about a year and a half ago at this point, policy distillation and actor mimic. And the goal in both of these papers, the domain that they're dealing with is Atari games. So they say, well, it's really great that you can use Q-learning, for example, to learn to play a particular Atari game, and you can use the same algorithm to play many different Atari games, but you can't get a single policy to play many different Atari games. And their hypothesis here is that if you can get a single policy to play all the Atari games, perhaps that policy can actually learn all the games together more quickly by sharing knowledge such as features or information across the games. All right, so before I get into that, let me present a little bit of background. This has nothing to do with reinforcement learning per se, but this is an idea that this method is going to draw on. And the idea is something called model distillation. These are some slides adapted from Jeff Hinton. And one of the things that's very useful in kind of practical applied machine learning, if you would like to build very good models for solving some complex problem, like some complex classification problem, if you can't build a single model that's really, really great at everything, what you can do is you can instead build many models that are kind of moderately competent and somehow combine them together. And there are many different ways of combining different models together, many different ensemble methods. And in general, most sort of like ML competition type things like Kaggle, many of the winning teams often use some kind of ensemble method on top of the latest and greatest machine learning techniques, whether it be neural nets or random forests or what have you. So this is something that is often not discussed as much in research papers, but in practical sort of applied machine learning, ensembles are great because you can take a soup of whatever different models you believe are good, fuse them all together, and get an even better combined model. The trouble is that ensemble methods are very expensive at test time. So if you want to run 100 different models instead of just your one best model, that takes a lot more compute, it takes a lot more memory storage, and it's generally a lot more unwieldy. So one idea that people asked a few years back is, well, can we make a single model that is as good as an ensemble? We built this ensemble. Somehow inside this ensemble, contained in this ensemble is the knowledge about how to do a really great job, for example, at a classification task. Can we somehow pull out this knowledge and bake it into a single, smaller neural network model? Right? The training set, that has all the data. Somehow, this ensemble has a little bit more knowledge in it. It has the knowledge for how to generalize from that data. So can we pull out that knowledge and stuff it into a single neural net? So this idea is called distillation. And distillation basically consists of training on the ensemble's predictions as soft targets. So instead of training on the labels in the training data, what you're going to do is you're going to take your training data, ask your ensemble to predict what it thinks are the labels, and it's going to predict a distribution, of course, because if you're doing classification, maybe you have a softmax at the top, and that gives you a distribution over labels. And then you'll use that distribution as soft labels. And this can work better for kind of a peculiar reason. So let me first explain how it works, and then I'll give you some intuition for why it might work better. So the way it works is that your model is going to produce some logits. These are the ZIs. And then you can, of course, evaluate the probability of a class, PI, using a softmax. You can put some temperature in there, so you can actually artificially smooth out the predictions from your ensemble. And then you can simply do your cross-entropy loss against the PIs, treating them as the probability of a particular class. So you no longer have a hard assignment of a class to each data point, you now have a soft assignment. Why is this a good idea? Well, the intuition is that there's more knowledge in the soft targets than there is in the hard labels. And that knowledge can help you generalize better. So these are MNIST digits. MNIST digits are a very standard data set for supervised learning, kind of little toy supervised learning benchmarks. And there are digits between 0 and 9, and you're supposed to look at the digit and figure out which digit it is. The funny thing is that some of these digits look a lot alike. Like if you look at this 2, it kind of looks like a 0. And if you ask a very good model, a model that is generalizing successfully, what it thinks this digit is, it'll say 70% it's a 2, 30% it's a 0. contained in that prediction is a lot of knowledge about digits. It's saying that, yeah, this is probably a 2, but when you see things like this, they should be kind of like, you should be thinking about zeros. So if it goes even more in the 0 direction, maybe if this little curve comes down a little further, then you should really start saying 0. Instead of overfitting to this crazy thing, saying that it's actually a 2 with 99% probability, but it's some kind of like really peculiar 2 that's in a different class of 2s from all the others. So the knowledge in that good, powerful model that's contained in these soft labels allows you to generalize better. If you can pull out that knowledge, use that as your labels, then you can get another smaller, much more well-behaved model to also generalize well. And this is the idea behind distillation. So now back to multitask transfer in RL. What we're going to do, and this discussion is mainly based on the actor-mimic work, but the policy distillation paper presents, broadly speaking, a similar idea. We're going to basically take this distillation idea and bring it into the world of reinforcement learning. So the setup is that we're, again, going to have an ensemble, but now it's an ensemble of policies that are all playing different games. So maybe we want to play the Space Invader, Sequest, Pong, and Breakout, and we'll have a different policy on each one. And these policies can be trained with whatever you want. So there's some kind of reinforcement learning algorithm that can allow you to train these. And then what you'll do is have a single policy. This is the actor-mimic network, since we're talking about the actor-mimic paper. And that single policy is going to be trained with distillation to have similar action distributions as the source policies. So the loss function for training the actor-mimic network looks like this. You sample your states and actions from your expert policy. So you're basically literally taking the data from the replay buffers of these policies if they're using Q-learning. And then you're just maximizing the log probability of those actions under the actor-mimic network, under the network that's, to which you're distilling. Now, in the original policy distillation and actor-mimic papers, the transfer is actually done in one-way fashion, where you actually train a single network on these multiple policies, and then at some point you take that policy and you deploy it back to the individual games. You can also go the other way. You can actually add log pi to the reward function for each of the individual policies here, so that both the learner policies are trying to match the global policy and the global policy is trying to mimic the local policies. This idea is very similar to guided policy search that we discussed before, and that also works fairly well. So this basically amounts to doing supervised learning. And it's analogous to guided policy search, but for transfer learning. So you can see a recap of that in the model-based RL slides. And then there are a few other details in which the actor-mimic paper and the policy distillation paper differ a little bit. Like they have a kind of a funny feature regression objective, so I won't get into that too much, but you can see the paper for the details. So there's a little more to it than that, but the high-level idea is on this slide. Yes?
Looks like this mostly applies to discrete domains. How would you turn it into something that would work more like in continuous?
Yeah, good question. So the question is, how could you do something like this in continuous domains? In continuous domains, you could do exactly the same thing. So in the actor-mimic paper, they do sum over all possible actions. If you have continuous actions, you would simply take the actions that were sampled during exploration. So you have some sort of integral here, and you're just approximating that integral with samples. Since the samples are drawn from pi e, you can actually like omit this term in here and just use the samples as training data essentially, which is by the way exactly what the guided policy search methods do. Okay, so sort of a lot of background theory on distillation, but in practice all we really end up with is supervised training on data from the policies, and in the particular case where we can enumerate all the actions, we can put the probabilities in here, and then we get this thing that looks like distillation. If we can't enumerate all the actions, then we can just sample them. Okay, does anybody have any questions about this? Yes?
So in the loss function, I saw that the sum is over A
Mm-hmm.
function, but it doesn't include the I, the index.
Yeah, sorry, this is a little sloppy notation. So this is for every single data point in the replay buffer. So you basically grab the replay buffers from all of these different learners. That gives you a big pile of states, and on all of them you do this objective. Any other questions? Okay. So here are some of the results from the actor-mimic paper. The policy distillation results, I don't have them in this slide deck, but it's kind of similar story. The blue curve, so the important curves to look at here are the blue curve and the red curve. So the red curve is training on a particular game from scratch, and the blue curve shows what happens. It's the same learner for everybody. So the blue curve is the performance of the combined policy on all of the games. So this sort of funny coupling, the red curves are all independent for different games, but the blue curves are actually all the same policy. So like over here and over here, this is the same policy. And you can see that the blue curve, in some cases, it does extremely well. So whatever it is that it gets from all these other games lets it just like completely nail breakout way faster than the independent learner. In some cases, you see negative transfer. So in Sequest, you can see that having this learner also trying to play all the other games makes it actually do quite a bit worse on Sequest. Now, there's quite a bit of nuance in this result, which is that Atari games are kind of a very peculiar domain for transfer, right? The games are all very different. Some of them are a little similar to each other. Some of them are not. So it's very reasonable that even a very, very good method would still see some amount of negative transfer, because there's going to be some games in the ensemble that are just not the same as the others, where the lessons that you learn from the other games are actually not a good idea in that game. But it's actually nice to see that there is quite a bit of positive transfer also over here and over here. Yes?
Do you have an idea why look at the Pong and the Breakout examples. Like the Pong one, the transfer, like I guess the multitask one is a lot more unstable, and then the Breakout one is a lot more stable.
Yeah. Yeah, so there's, I can't exactly tell you why that particular instability is happening, but there is one nuance with these distillation methods that's worth keeping in mind. And that's coming back to our imitation learning lecture. So when we talked about imitation learning at the very beginning of the course, we talked about this problem of domain shift, which is that imitation learning by itself does not guarantee a good expected reward, because when you run the supervised learn policy, it will not visit the same states. And that is very much a problem with these distillation-based methods, is that you can do supervised training on a bunch of source domains, but there's nothing that's guaranteeing that supervised learning process actually produce good results. In the Actor Mimic paper, they actually discussed using a variant of Dagger to try to mitigate this problem, but they do it for a very small number of iterations and sort of not, they don't try very hard, so to speak. Although in principle, that could go a long way towards addressing this problem. The other thing that could probably go a long way towards addressing it is to actually include this log pi AMN term in the reward for the individual learner policies, which was not done in these results, but in principle could be added. And there's more recent work that does look at doing that as well a little bit. Okay, any other questions about this? All right. So now coming back to the question that, that was asked before about how does the model know what to do. So far, what to do, which game to play is apparent from the input. So if you see a screen of Breakout, you know that you need to play Breakout. But what if you want to build a policy that can do multiple things in the same environment? So in general, you might imagine you might have a robot, and that robot comes into your home, and today it's supposed to do the laundry, but tomorrow it's supposed to do the dishes. Somebody needs to be able to tell the policy which task it's supposed to perform if it's not readily apparent from the observations already available. So there's some kind of context, omega, and there's one context for doing the dishes and a different context for doing the laundry. So this kind of setup is sometimes referred to as contextual policies. And contextual policies have been a particularly popular formalism in robotics and computer graphics. So contextual policies are a very, very simple idea. A standard policy gives you a distribution over actions conditioned on states. A contextual policy gives you a distribution over actions conditioned on states and a context. And the context is no different from a state in any way whatsoever. So the context tells you do the dishes or do the laundry. Maybe it's a number, maybe it's a discrete value or a continuous value, whatever you feel is the right way to parameterize your task, and it is just part of the state space. So you simply redefine your state space to be S tilde, which is your original space, and omega, and the combined state space is just a concatenation of the original one and the space of context. And that's it. There's a little bit of additional kind of cleverness you can do if you know that part of the state space is a context, because contexts don't change during execution. So no matter which action you take, you will not change the context. And you can exploit that a little bit in some ways, but the simplest and oftentimes very effective thing to do is to simply make the context part of the state, forget about it, and just do the thing normally. And then you're basically back to the Atari setup. Now there's something in your observation space that tells you what you're supposed to be doing, and you can stop worrying about it. So a few examples of works on contextual policies, or I guess these are a few examples of contexts. So here you have a robot stacking a Lego block. There the context might be the location at which it's supposed to stack that block. Here you have this is a computer graphics project. You have a little humanoid trying to walk, and the context is the direction you want it to walk, which is indicated by the user. Here you have a robot hitting a puck, and the context is where should that puck be hit to, what's the destination, and so on and so on. So just a little number, either discrete or continuous, that you can add to your state, disambiguates the task to the policy and tells it what to do, and it can also provide a very convenient lever for, let's say, a human user to command your system to get it to do the thing that they want. So it's a very simple formalism, and that basically resolves the ambiguity. And the term contextual policies is sort of inspired by the term contextual bandit, where you give a little piece of state as input for conditioning. We'll actually come back to contextual policies when we talk about meta-learning next time, where there will be actually an interesting connection between meta-learning algorithms and contextual policies. But for now, I'll leave this as is, a very simple idea that allows you to disambiguate which task you're supposed to do that can simply be plugged into any other multitask transfer method. Okay, any questions about contextual policies? Yes?
Not exactly about contextual policies, but in general, like if you're transferring like multiple tasks, but they involve different degrees of freedom, then how's it even done?
Yes, so that is a very good question. So far, everything I've discussed assumes that the state space, at least the state space dimensionality, does not change between tasks. There are a number of ways to handle different state dimensionalities that are based around either embedding or modularity. I'll actually discuss modularity in this lecture. I won't talk about embeddings, but we can talk about those offline afterwards. And actually, modularity is the next thing I was going to discuss. So let's talk about architectures for multitask transfer. So far, all the methods I've discussed deal with generic deep neural network architectures. If you remember at the beginning, at the end of the forward transfer section, I talked about architectures for forward transfer. Now let's talk a little bit about architectures for multitask transfer. So far, it's a single neural network for all the tasks, at least in the end, in the case of the distillation method. But what if all the tasks have some shared parts and some distinct parts, and you know which parts are shared and which parts are distinct? So for example, let's say that you have your different tasks are driving two different cars, and then actually for each car you might want to drive it in different cities. So I want to drive a car equipped with a camera in Los Angeles and a car equipped with LiDAR in New York, and maybe the LiDAR equipped car also has some experience in Los Angeles, but the camera one does not have any experience in New York, and I perform some transfer between these. So two different cars, two different sensors, and two different cities, but I haven't seen all possible combinations. Another example, I have maybe 10 robots trying to do 10 different tasks. One of the robots has seen all 10. Another one has seen just 2 of them. It seems like there's some robot-specific things that they can do. Maybe one of the robots has a suction cup, another one has a little gripper, but somehow the experience of actually touching these different objects, there still should be some transferable bits there. So these are the kind of settings we're going to study next. And the question that we want to answer is, can we design architectures with reusable components? So reusable components are a very good idea in traditional engineering. If you want to design, let's say, a motion planning method, you want that motion planning method to work for all sorts of different systems in a generic way, and then you can plug it in as a module with whatever kind of low-level controller you have sitting underneath it. If you want to design a dynamic programming algorithm for your inventory management system, maybe you want the same dynamic programming algorithm to be plugged into whatever kind of warehouse automation system you have. So modular components are very useful when you're manually engineering things. Can we have modular components when you're learning policies? So we're going to discuss this thing called modular policies, where the idea is to have a deep neural network policy that actually consists of multiple parts, and some of the parts are reused for different tasks and some aren't. So you might have, let's say, a policy consisting of 2 parts. The green part might be used for 2 different tasks, but then combined with a different yellow or orange part to specify to the particular task it's supposed to be doing. So let me give a more concrete example, and this is from a paper by Devon and Gupta. Let's say that you have a variety of different tasks for your little home automation robot, and maybe you wanted to open your drawer for you to get your clothes, and you wanted to push some heavy object out of the way so that you can rearrange your furniture. And you have your company sells different kinds of robots. It sells a robot with 3 links and a robot with 4 links. So now these systems simply have different state spaces. This one and this one, you can't give their inputs to the same policy. So this gives rise to a matrix of possible combinations. You might have 3-link robot opening the drawer, 4-link robot pushing the block, and any possible combination. One thing we could imagine doing is training a single policy for all the tasks, or a single monolithic policy for each task, right? But if we know that there's some structure here, so the way that the 4-link robot moves is going to be kind of similar regardless of what it's doing, but different from the 3-link robot, and the physics of the block being pushed might be similar for the two robots, but different from the drawer, we can actually exploit that property to build a network that's made of modules. So we can say that we'll have, in this case, maybe a robot-specific and a task-specific module, because those are the factors of variation in our problem. So then we might have a 3-link robot green module that's used whenever you're using the 3-link robot, and downstream from it might be a task module that is specific to that task. So if we're doing the 4-link robot with a block, we use the blue module and the orange one. If we're using the 3-link robot to move the block, we use the green module and the orange one. And the interesting thing about these modular networks is that in conventional kind of engineering, when we're designing systems made up of modules, we have to manually specify the interface between the modules. We say, oh, the way that your motion planner will communicate with your controller is by providing joint angles. Since these modules are all learned, the interface between them can actually be learned as well. So what you can actually do is you can set up these modules, and you just say, it's the same one here and here, but you don't say anything about what goes between them. You simply have your green layers and your orange layers, you attach them together, and then you just train them end to end, and their interface is a learned vector of activations. That's a very reasonable idea, and it actually tends to work pretty well, but it has a little bit of a challenge, which is that it's quite prone to overfitting. In particular, if you have a small number, in this case of robots and tasks, especially if you have just two, you have a pretty substantial risk that the green module will just learn to output, half of its representation will be for drawers and half will be for blocks, and nothing there will be shared. What you'd really like is you'd like the for example, the task component to say, oh, it's time to move this thing, and the robot component to figure out how to actually move that thing in that particular way. So you want sharing, you want some amount of compression in that interface. And that's one of the bigger challenges when it comes to modular networks. Modular neural networks research in computer vision and NLP has looked at regularizing the interfaces by explicitly supervising them, by saying that, oh, I want the interface to represent this piece of information. In reinforcement learning, people have also looked at regularizing these interfaces through standard neural network regularization methods like dropout, which try to basically build redundancy into the interface and thereby prevent it from overfitting and specializing in this way. But in general, regularizing these things is kind of an open question, and there isn't a single perfect solution, other than using a very large number of tasks, or a very large number in this case of robots. Okay, so that's the basic idea behind modular networks. Does anybody have any questions about this? Yes?
So do you train them simultaneously, or do you train like one and then next and then the next?
So in this particular work, they're all trained simultaneously. So the setup is that there is, let's say, a number of training settings. Maybe the 3-link robot has seen both the drawer and the block, but the 4-link one only gets to see the drawer. And the training settings are all trained simultaneously, end to end. And then you can combine novel combinations of these modules on a test setting. And for the test setting, there also you can consider either zero-shot transfer or few-shot transfer. So in zero-shot transfer, just like before, means that you just directly combine these modules, run them, and hope for the best. But if the combination is a little too different from what was seen before, you might also have few-shot transfer where you actually fine-tune them together on the test task. Okay. So let me show a little example from the evaluation in that particular paper. So they're considering this kind of multi-robot, multitask setup, where there's a robot with 3 links, a robot with 3 links, but one of them is a little bit longer, and a robot with 4 links. And they're trying to do different things, reaching for a little white square, pushing an object to a point, and inserting a peg into a little hole, kind of like a little simulated industrial assembly task. And then the idea is that here, because the number of tasks is fairly small, it's again a hold one out sort of setup where it's training on all these tasks and then testing on just one of them that is not seen during training. Of course, in reality, if you have a very large number of tasks, then you would presumably have more unseen tasks. And here's a little illustration. So this is showing the zero-shot combination. It's not perfect, so sometimes it gets pretty close. It generally has the right idea of the task, but is obviously not as good as the individual training settings. And then you can fine-tune from there and get slightly better performance. OK. So summary of multitask learning. More tasks equals more diversity equals better transfer. So sort of similar story in general as what we saw in the discussion of forward transfer. It's often easier to obtain multiple different but relevant prior tasks than it is to manually design a highly diverse source domain for the particular task that you want. So in many cases, it is quite relevant to consider multitask transfer. We can think about doing it with model-based RL, where we sort of try to pick out the invariance across all the different source tasks, which typically is something like the equivalent of the laws of physics in your domain. You can think about distillation, which is a way to combine multiple policies into one for concurrent multitask learning, where you're learning multiple tasks simultaneously and you'd like to accelerate all of them through sharing of information. If you have a setting where the observation alone is not enough to figure out what you're supposed to be doing, then you can consider adding a context and getting a contextual policy where it gets an additional variable appended to the state to tell it which task it's supposed to be performing. And then if you want to consider architecture specific for multitask learning, or if you have settings where the different tasks have, for example, different state dimensionalities, you can look into modular networks and ways to design these reusable components that can be shared across different tasks. OK, any questions about this? All right. So some suggested readings. These are, again, all the papers that I've discussed in this lecture on multitask learning. This is the model-based paper that I covered. This is the policy distillation paper, and this is the actor mimic paper. So these two do reasonably similar things. They're a little bit different in the details, so if you are interested in distillation, I do recommend checking out both of those. This is the modular networks paper. And then there is some additional work on transfer that I didn't cover, like learning shared feature spaces. And if anybody's interested on that, please do let me know. OK, so that's it for today. On Wednesday, I'll get into multitask meta learning, where we actually have a multitask setup, but instead of just trying to figure out how to accelerate the learning of those tasks, you're actually trying to use them to learn how to learn faster, which is, in a subtle but very important way, different from the multitask topics that we talked about so far. And then on Wednesday, I'll also talk about some challenges and open problems to conclude this portion of the course. So I'll see you all then.
About you mentioned the shared feature spaces. So yeah, I would think, like